Yeah, thank you very much. It's a pleasure to speak here at JuliaCon Local in Paris. I'm going to talk about sampling the eigenstates of an infinite dimensional matrix with Rimu.jl. Right, so what motivates us? What are we interested in? We're physicists. We want to solve quantum many-body problems, right? So the original motivation for this is we want to solve the Schrödinger equation. So we have actually these, 4 different things that can all be done with these quantum Monte Carlo algorithm. I'm going to focus on the first one here, time-independent Schrödinger equation, and the motivation for that may come from solid-state physics, quantum chemistry, or nuclear physics, for example. Right? My personal interest of my research group is mostly the physics of ultra-cold atoms and, strongly correlated quantum many-body systems that can be emulated with those. Right. So full configuration interaction quantum Monte Carlo is a fairly modern flavor of projector quantum Monte Carlo. The aim of projector quantum Monte Carlo is, yes, to find the ground state and maybe some low-lying eigenstates of a large quantum many-body Hamiltonian without any approximations, but then sampling it stochastically. Now, the history of this is that the idea is fairly old. So, last century, this was done in the context of atomic physics and nuclear physics initially, and then, moved into quantum chemistry, maybe, and solid-state physics. And so we're going to use and implement an algorithm that is fairly recent, so from 2009. So what is the principles of what we're doing is, yes, we're solving this. First of all, we represent the Hamiltonian as a matrix. So that turns the Schrödinger equation into a generic linear algebra problem. So it's really finding the eigenpairs, the eigenvector and eigenstate of a large matrix. Typically, this matrix is sparse if you represent it as a matrix. As you can see here, this sparsity pattern. Now, we don't actually store the elements of the matrix itself because we're assuming eventually it will be very large. And often we're not even able to store the vectors or all the vector elements. Now, the package I'm going to talk about implements both exact diagonalization, where we have to store the vector and we do everything exactly deterministically, and then we're going to do it in a stochastic way where we sample the whole thing and we only store some sample of non-zero elements. So the idea is that this iterative procedure, which will eventually lead us to the ground state and its energy, is done in a stochastic way. So instead of doing a proper vector matrix multiplication, we do do just some of the operations, but we do it in such a way that by expectation value, we're doing a proper matrix vector multiplication. In particular, at the end, we're doing a stochastic vector compression, actually quite similar to the example that we saw this morning about stochastic rounding of numbers. We're doing very similar thing, and then we only store the non-zero elements of the vector. This is how we can solve this problem, even though we can't afford to store all the vector elements. So what is Rimu? It's a native tree in New Zealand, but actually here, of course, it's a different thing. It's random integrators for quantum many-body systems, right? So we've been working on this Julia package. It's sort of a Julia re-implementation of an algorithm there. The only other free software that exists out there is written in Fortran. So we have a pure Julia implementation. Your previous code was written specifically for quantum chemistry problems. So this is a bit more general, allows you to treat bosonic, fermionic quantum particles. We're aiming to have this much more general and do more things. Right, so I gave a talk at JuliaCon last year. So what's new since then? So we have revised some internals, in particular the abstract Hamiltonian interface. It's now easier to generate your own model Hamiltonian because you can now add already existing Hamiltonians, products and wrappers for abstract Hamiltonians. We have a very efficient way of mapping this, wrapping this as a linear map, which made it much faster to do matrix-free vector multiplication and then matrix-free exact diagonalization, where we can just use existing Julia packages for that. So that allowed us to successfully diagonalize fully deterministically a Hilbert space with dimension 10 to the 9, right? So 10 to the 9 is you can just store the vector if you have enough memory, but you can't really store the matrix elements. Right, we implemented sampling, calculating excited states, and then the two things that I want to mention in a bit more detail is sampling a project where we sampled an actually infinite Fock space, and the second project is a recent Julia Summer of Code project, interfacing this with some quantum chemistry software. Right, so how can we sample an infinite space? So specifically, now I'm talking about a physical model, which is the Fröhlich polaron model. It's a very old model looked at by Landau and Pekar in the 1930s, and then famously Richard Feynman had great success with his path integral method of finding a variational approximation to this. It describes the motion of an electron, slow-moving electron in a polarizable medium, modeled by a bath of phonons. So the electron dispersion is then modified, and so it looks like that. It becomes gets an effective mass. There's a continuum of phonon excitations in here, and quite recently, a couple of mathematicians that we collaborate with have proven mathematically that in the limit of infinite coupling, there exist these additional bound states where sort of the electron has excited states of the phonon dressing cloud, but they didn't know at which coupling constant does this actually appear, because at weak coupling they don't exist, at very strong coupling they do exist. Now, because the model is formulated in an infinite dimensional Fock space, the dimension technically here is huge, so you couldn't represent it. We have to target bound states, and there's a Monte Carlo sign problem that we're able to overcome, and here's a result. The publication is on arXiv, so we see here the continuum being pierced by this bound excited state, which appears at fairly moderate value of this coupling, dimensionless coupling strength. I just want to mention, last we had recently a Google Summer of Code project to implement molecular Hamiltonian. That's basically implementing an interface between our code, Rimu.jl, and a quantum chemistry package, ElemCo.jl, which does, what quantum chemistry does, so self-consistent field, Hartree-Fock calculation, can also do some post-Hartree-Fock, like coupled cluster calculations, and now with molecular Hamiltonian, you can input the data into Rimu and then do full CI quantum Monte Carlo on molecular Hamiltonians as well. So with that, I'd like to thank for the funding and show a picture of people involved in this group, in this work. Thank you very much for your attention.
So, do you have any questions? Maybe I just have one question, but I'm really not an expert. But you showed that you transformed the problem into a linear algebra problem. But I was wondering if you can put some optimization somewhere, and where. And
I can put, sorry?
So some optimization somewhere. You can.
Optimization problems. Yeah, I don't know. So if they can be formulated in, well, would have to think about what kind of optimization problem. So it is really, it's eigenvalues of a linear operator, yeah, which is what we're finding. Not sure how this would, but happy to talk afterwards about how this could apply to optimization problems.
Okay.